Hello, welcome to this session on prime numbers. We're going to try and prove that there are an infinite number of prime numbers. Now this is a proof by contradiction that is on the A-level syllabus. However, it's one that we're very good at reproducing, but I don't think we're really that good at understanding it. I'm going to try to help you understand this by using a concrete example. So I'm going to make the outlandish claim that there are only 4 prime numbers in the world, and they are 2, 3, 5 and 7. Well, those are our prime numbers. If I've got a composite number, let's say 12, I can say okay, 3, 4, I can draw a factor tree. If I've got a composite number, I can always draw a factor tree. It's a nice way of looking at it. Let's think about, shall we say 70? I've got 2, 35, and I've got 5 and 7. Just a couple of examples. And I can always divide composite numbers by one of my primes. If I can't divide my composite number by one of my primes, then it's not a composite number. It's a prime. Now let's play a little game with this. I'm going to multiply all these together. I'm going to say 2 times 3 times 5 times 7. And that gives me 210. I'm going to add 1. And I get 211. So what I've done is I've multiplied all my primes together and I've added 1 to get 211. And I'm going to investigate what happens if I divide my number 211 by the primes in my prime family. I'm going to go through all the primes that exist in the world according to me and divide them. So 2's into 211 is 105, remainder 1. So it doesn't go in, does it? 2 doesn't go into it. Let's try 3. 3's into 211 is, that's right, 70, remainder 1. Let's try this. 5's into 211. It's actually 42, remainder 1. And we're seeing a bit of a pattern here, I think. What about 7's into 211? 30, remainder 1. So a number of interesting things happens here. I always get a remainder of 1 when I try to divide by my primes. And the numbers I get are quite interesting. Okay, yeah, the numbers we get are 105, 70, 42 and 30. What happens is 105 is 3 times 5 times 7. These 3 numbers. 70 is 2 times 5 times 7. 42 is 2 times 3 times 7. And 30 is 2 times 3 times 5. So what would happen is if I divided 210 by any of these, I would get 105, 70, 42 and 30 with no remainder. If I divide 210 by 7, I get 2 times 3 times 5. 30. If I divide 210 by 5, I get 2 times 3 times 7. 42. And something similar happens with 210, but I get that remainder of 1, of course. And something maybe we overlook. Well, what is a remainder really? Well, it's what you get when you left over when you try and divide a number into something. It doesn't quite go. Well, the remainder 1 means these numbers are dividing into 210. Well, what is the relevance here? Why am I doing all this? Well, what this means is 211 cannot be divided by 2, 3, 5, and 7. I have said those are the only prime numbers. Now, that means 211, according to me, must be a composite number. However, if it's a composite number, I'd be able to do a factor tree. I'd be able to divide it by one of these, but I can't. So that leaves one of 2 possibilities. 1, 211 is actually a prime number. The other one is that I can divide 211 by some other prime number that I've not mentioned already. Either way, these are not the only prime numbers. Way 1, 211 is actually a prime number, then I was wrong about these being the only prime numbers. If it is a composite number, then there must be another prime number. That's not 2, not 3, not 5, not 7 that goes into it. Well, in fact, 211 is a prime number. You can easily find that. But the principle is, I've proved it using the definition of prime numbers, using the idea of what a composite number is and what a prime number is. And this is the reason why our proof for an infinite number of prime numbers works. So let's actually do that now. Let's do that now. So I'm going to prove by contradiction that there are an infinite number of primes. So we're doing a proof by contradiction, so I've got to do my steps. So my first step is my assumption. I have to write an assumption. I assume that there are a finite number of primes. Helps if I write assume correctly. Number of primes. So I assume that there are a finite number of primes. I'm assuming the opposite. That's how proof by contradiction works. The next step. The primes that exist are, let's call them P1, P2, P3, etc., all the way up to Pn, which is the last prime. And that's what I did before. I made that assumption with just 4 primes. Now we're generalizing, we're saying I can have n primes. Now, let n equal P1, P2 times P3 all the way up to Pn, add 1. So that's like my 210 add 1 from the previous example. That's like my 211. Now, when you divide n by any of the stated prime numbers, P1, P2, all the way up to Pn, you will naturally get a remainder of 1. Just like when I divided 211 by 2, then by 3, then by 5, then by 7. Because if I divide n by one of these, I'll get the product of all the other primes with a remainder of 1. That's how division works. Now, this tells me none of the stated primes, P1, P2, all the way up to Pn, are a factor of n. So I've created a number for which none of my primes are a factor. I've said that this many primes, just like 211 this time, I've got n. So what does this mean? This means that n must either be prime, because nothing can go into it, none of the primes can go into it. Just imagine one goes into it, and n itself, or there is another prime that is a factor of n, which is not in my list. Either way, there is another prime, and this is a contradiction. I've contradicted my assumptions. Therefore, there are an infinite number of primes. Well, let's see what I'm saying. Let's compare it to my work. So, prove by contradiction that there are an infinite number of primes. Well, I did that over here with a simple version. So I did a concrete example. I kind of proved that there are more primes than these. Well, assume that there are a finite number of primes, and they are P1, P2, P3, all the way up to Pn. Well, I did that with 2, 3, 5, and 7. It's not quite as generalized as this proof, but I've done it. I then created this number here, n, which is the product of all those primes add 1. Well, that's what I did with 210, and added 1 to get 211. This is sometimes the bit where people don't quite understand. So when you divide n by any of the stated primes, you get a remainder of 1. Well, the beauty of a concrete example, I can just show why that is the case. Theoretically, I could do that with all the primes I've listed. So none of the stated primes are a factor of n. So in my case, 2, 3, 5, and 7, they were not a factor of 211. So here's where the contradiction comes. So n must be prime, or there must be another prime I've forgotten to list. That's not in my list. Either way, there is another prime, and it's a contradiction. Therefore, there are an infinite number of primes. Well, why does this work? Why does this show? Well, my list there, every time I add another prime to it, if I do find another prime, I just add one and I get the same result again. I will always find another prime. This logic tells me there's every time you think you found all the primes, there's still more. Now I know I've gone on a bit there, but I hope that makes that a little bit clearer. Thank you.